This is a presentation called Overcoming Unscientific Opposing Arguments Using Relevant Data. I want to begin with this picture. This is the type of validation picture that it appears all the time in studies. They started becoming popular around 12 years ago. And here the purpose is to show the specificity of a method of genotyping. So philosophically, what are we looking at? Imagine that we have a population of probabilistic genotypes from a lab. And we want, and say there are 2 and 3 person contributors, and we're looking at genotypes that are separated out from them, that are known up to probability. And what we want to know is to what extent, if we compare these genotypes with the wrong person, the person who's not actually in the mixture, how can we determine that? And the way we often do this in statistics and science is we develop a score, a number. You all know what a score is, right? You go to the doctor and they run these tests. You get 24 scores, your calcium level, your glucose. You get these numbers. And nowadays you probably get little bell curves or confidence intervals that tell you to what extent you're within the normal range, right? You all know what I'm talking about, right? So in forensics, we want a classifier to do something like that. Like in medicine, does somebody have the disease or not? Right? Is this a good restaurant? Isn't it? So we're used to scores, scales of 1 to 5, numbers, quantitative, whatever. In forensics, the score that's used is the likelihood ratio, and it's used a lot. It gained popularity about 25 years ago in many different areas of forensic science, including DNA. It's a fine score. People like it because it has some nice rhetorical properties, and it also has some nice mathematical properties. It's not the only score you could use, but it's a pretty good one, and it has a lot of nice information properties. So what we're looking at here is a score. How do you get a score? You take evidence and you from a genotype. You take a genotype derived from some physical evidence, and you compare it with another genotype. They could both be probabilistic. They could both be definite. Typically in casework, one is probabilistic from the evidence, the other might be definite as a reference sample. Like a point probe in physics or math or something. And you make a comparison between this fuzzy evidence genotype and this definite reference genotype. And that comparison calculates a likelihood ratio, which mathematically, the easiest way it's been understood for about 100 years is the change in probability. What did you believe before you started about how likely it was that this person's DNA might be present in a sample? And after you look at the data, now what's the probability? And that ratio of probabilities of after to before is one of the probably the most common way outside of forensic science of understanding a likelihood ratio. There are about 10 different ways I know of to write it down mathematically, but the change in probability is the most pervasive one in science. Regardless, you get a number telling you what is the data trying to tell you about this hypothesis. How much has it changed the probability? Because the likelihood ratios can range from 10 to the minus 30th, like it does here. So here's 10 to the negative 30th. Here would be 10 to the positive 30th. You put everything on a logarithmic scale so you can see everything. But the log scale has another nice property that it makes everything with information additive. So the likelihood ratio is not additive, it's multiplicative. But the log likelihood ratio, the logarithm, is additive. That means you can add up the logarithms at every locus and get the total. And when it's additive, that means you have things like bell curves. So additive properties are very good in statistics and math. So for the rest of this talk, I'll be working like most forensic scientists do on a logarithmic scale. It makes no difference, by the way, from what I'm talking about with error rates and so on in classification, whether you're on a log scale or a linear scale. It's just easier to see. So here's a classifier, and the question is, when we compare evidence against a non-contributor, somebody who didn't leave their DNA, can we correctly classify them as not being there? Do we get a negative number? Negative number being a likelihood ratio less than 1, right? Because the logarithm of a number that's less than 1 is negative. And how good is that classifier? To what extent do we get numbers greater than 0? Or whatever threshold we use. With likelihood ratios, log LRs, you usually use 0. So we're trying to take a genotype from evidence, compare it with a person, and ask the question, to what extent, summarized in one number, is all this data trying to tell us and classify for us whether somebody is a contributor or non-contributor? So here's an experiment where, with Virginia, we took from their lab 100 or so evidence genotypes that were uniformly distributed, as we show in this paper. It's really a fun paper if you want to read it. It's at +1. It's available for free, peer-reviewed journal. We used to do a lot of our hearings just based on this paper because there's so much in it, and it's pretty understandable. So we have easy cases, hard cases. We have genotypes that are 5% of a mixture, other that are 95%, everything in between. Very representative. And what we see is a distribution of exclusionary statistics. So what we did is we compared those 100 genotypes from evidence with 10,000 references that were randomly generated. That is, they're not part of this evidence. And we got 1 million LR calculations, and we sampled 1 million log LR values and plotted them in a histogram. And what we see is that this classifier, this log LR score, for this Virginia data, did a pretty good job of classifying. Virtually all of these numbers are less than 0. Here's 0. Less than 0. The average is -18, which is 1 over a billion billion. And when you get that number, if it's negative, you can pretty much rely on the person's not being there. And the false positive rate is very, very small. The area under the curve, the bars you get beyond 0, I think once you get up to maybe a match statistic of 100, it's 1 in a million, and then it completely disappears. Okay? The area under the curve corresponds to a probability. Why? You're looking at it. Here's a distribution. Probability is the area under a curve of a probability distribution. Let's think of a probabilistic genotyping system as something that's working as a classifier. It takes the data from the evidence, it produces this probabilistic genotype, and when it's compared with 1, 100, or in this case, each one with 10,000 references, it produces scores. And if it's a good classifier, the scores will be clearly less than 0. And if it's a bad classifier, well, we'll see what happens for inclusions as well, but we won't be able to make much of a distinction. Here it's a good distinction. This shows that TrueAllele is very specific on the Virginia lab, on this data set, because the population of these 100 genotypes is producing negative scores. That's what we're seeing. So think, there's an actual population of genotypes. We measure it. It produces negative scores. That lends credence to the idea that if we look at genotypes in the future that are new, they should also have negative scores if somebody's is not there and they're non-contributors. So we're going to look at genotyping as a classification problem. What are the distributions of non-contributor log LR scores? Here they're all negative. And first, let's make a statement. This is 1 million LR calculations from 100 genotypes against 10,000 random references. What if we compared the same 100 genotypes against all trillion possible genotypes, weighted by their appearance in the populations, that is, non-contributors? Well, it turns out you can do that, and in a method that's a lot like the binomial distribution tricks in probability with convolution. You don't have to do any LR calculations, and you can calculate the exact distribution of each genotype against all trillion references, and then basically average them together. And that, done mathematically in about a minute, is the same picture as what we published, taking months to do 1 million comparisons, collate the data, and so on a mere million samples, as opposed to 100 times a trillion, and getting an exact answer. If you're okay with probability and math, this is a wonderful paper. If you hate math, or you have to read every line of probability equations you don't understand, don't read this paper. Or just look at the pictures and read the introduction and the conclusion. But people who have had an undergraduate class in probability and know what a random variable is have loved this paper because it's really clear that there's no magic. You can get the complete distribution here of the non-contributors just using some basic probability, discrete probability, and a method known as convolution that's been around for 350 years. That's used for everything. In fact, convolution was used as the basis of doing fast Fourier transforms using fast convolution algorithms instead, like in the 1980s. There's a whole literature on that. It's been around for a long time. I won't talk about convolution, but there it is. So you see this, the concept of classifying, the idea that we can calculate an exact non-contributor distribution instantly just from the genotypes without even making a comparison. What does that tell you? That the information about what the distribution of a genotype is inherent in a probabilistic genotype. And the reason is because the likelihood ratio is measuring the change from the population distribution to an evidence distribution, the prior probability to the posterior probability. This is just based on standard math, saying there's only two probability distributions involved in the likelihood ratio. The prior, before you saw the data, that's the population, people who didn't contribute DNA, and the posterior distribution of genotypes, of what the genotypes look like after. And then you've seen evidence. And then you do some math tricks that are explained in papers like this to get these distributions. Now it turns out this is what the contributor distribution looks like. Using the methods of this paper, we don't need to compare with 10,000 references. We can compare with everything instantly and just get the answer exactly. And we can do it not just for the non-contributor distribution of random population, we can do it with the distribution of genotypes, the probabilities of the evidence genotypes. That is, after you look at data, probability gets concentrated to certain genotypes and less probability on others. That's the distributions we're talking about. What also this means is that if you have a contributor, if this is the population for Virginia on the 100 samples of the scores, the log LR scores, the population of these 100 samples are centered around 12, which would be about 1 trillion. This is the distribution of what you can expect the likelihood log LRs to look like, and there's not much overlap. In fact, TrueAllele in Virginia producing a log LR value on its normal evidence, 2 and 3 contributors, say 10 years ago, against a reference, will give you a score. And that score, whether it's positive or negative, will cleanly separate whether somebody left their DNA as a contributor or they didn't. We're looking at the log LR as a classifier. And it's a pretty good classifier on this data set because there's essentially virtually no overlap between the distributions. A positive score should mean a contributor, and a negative score should mean a non-contributor based on this validation study. That's our starting point. I want you to understand this classification, the contributors, the non-contributors. We can calculate them in a minute on a computer exactly. as if we had compared with a trillion. Now we can start with the arguments. These are all arguments that appear in court, in papers, by defense experts like Thompson. Basically, they're opposition arguments that are made to... They're also made sometimes by people in government who want more money for their agency. They raise these red herrings. And the question is, how do you answer them? And what we've learned over the last decade is how to answer them using these distributions, which I'm going to cast into the language of statistical classification. Is somebody in or somebody out? Is their DNA in the DNA? Is it not in the DNA? Is it in the evidence, not in the evidence? We're trying to classify statistically. But here's a really popular argument. I've heard it made by government laboratories who wanted to get, honestly, $14 million in a particular report to do lots of ground truth laboratory experiments to validate probability. So you do a lot of experiments. What is that telling you? Well, what does ground truth mean? Ground truth means that you're doing an experiment where you know the answer. You think you know. Actually, we've seen studies where people have made mistakes in the lab. But you believe you know the answer. You know the correct genotype that this evidence is matching to. You know the reference. You know the evidence. You've compared them. And when you compare them, you know what the answer should be. A lot of problems with that because maybe there's so little DNA that the laboratory isn't even generating enough data that anything could detect it. So it's not a great argument. But the idea is, how could you possibly understand the reliability of these PGS systems, TrueAllele and so on, star mix, Euro 4 mix, if you don't know the answer? Well, if you have LR distributions, it's really not a problem. Let's talk about classification. We just saw in the bottom right something like this. We have a classifier. Let's call it a log LR score. And we would ideally want to completely separate the distribution on the right from the distribution on the left, and the score would tell us what's going on. That would be a pretty good classifier. On the other hand, imagine that the curves were the same and there was no separation and you got exactly the same distribution for contributors and non-contributors. That would have no information. So a standard way that classification accuracy is measured in all of science, but particularly more recently in machine learning, artificial intelligence, and statistical fields, is to look at A. It has different names, but sometimes called A prime and has various names. Let's call A for accuracy, classification accuracy. Classification accuracy. If I were to sample from the left distribution and sample from the right distribution, I would get two numbers. A log LR from red on the left, a log LR from right in blue. What's the probability that the left number will be less than the right number? That the log LR will be less from one distribution, the left, than from the right. That's A, the accuracy. It's for sampling left and right scores. There's a way of calculating exactly that doesn't involve sampling. That's what we're going to use. But I'm not going into the math. It's also standard math that's been around since the 1950s. Nothing really new here except how we're going to apply it. So let's see how this works. If the two distributions for non-contributor and contributor, or disease and not disease, overlap, you see that that probability of accuracy is 50%. Half the time you're going to sample two numbers and one's going to be less than the other half the time it's going to be the other way around. So 50% is the rock bottom for anything that even is slightly accurate. What if the distributions are completely separated? Sampling from the left, and you'll get a negative number, and on the right you'll get a positive number from an actual contributor. So the probability of left being less than right is 100% because the distributions don't overlap. And so the accuracy in that case is 1. And in between, it's in between. This is what it looks like for bell curves when A is At this amount it's like 3/4. Here it's 98% when they get closer. So you get this spectrum of classification accuracy. I'm going to use this concept applied to the non-contributor distribution, here on the red on the left, and the contributor, the blue on the right, with the log LR, and we'll talk about not just looking at these distributions, but calculating the classification accuracy. Notice that if the classification accuracy is 75%, then the chance of inaccuracy is 25%. Just take 1 minus that. It's a probability. All right, so what we saw with the Virginia study, when the accuracy is 1, it's called a perfect classifier. And when you calculate A, the accuracy measure, it's 1. This is an accurate classifier. If you were to sample from somebody who didn't leave their DNA and somebody who did leave their DNA, the probability that those numbers would be in the correct negative-positive order is basically 1. That's a good classifier. This is TrueAllele on Virginia data over 10 years ago. In that paper, what we wrote is this is how you validate on casework data that's not ground truth. These are the words. I'll explain. Since the TrueAllele method's high specificity assures the identification hypothesis with certainty, that means that if you look on the left, if you get a negative value with very high probability, a non-contributor, if you get a positive score, the left distribution is telling you it's very unlikely that it's a false positive. That's what we're saying. Because the specificity, the error rate of false positive matches is incredibly low. Therefore, you can study the contributor distribution safely. You don't need ground truth because you have the error rate from the left distribution of non-contributors telling you that when you see a positive score, it's really almost always a contributor. Therefore, you can safely look at the sensitivity of the positive scores without knowing what's coming out of the genotype distributions. You don't need to actually have it make a comparison with anyone. Conversely, if you know that your method is sensitive and that your contributor distribution is concentrated to the right of 0, that exclusionary scores are to the left, and so you can safely examine negative log LR values. So you don't need ground truth if you have a good classifier. You can quantify how often, based on area under the curve and error rate, that it would be unsafe, and the probability is very low. They mutually reinforce each other. So you don't need to actually know what the answer is, and you don't need to spend $14 million giving it to a government agency to do all these ground truth studies, because mathematically it's silly. Here's an interesting case. This was in Louisiana, New Orleans, 2013. Armed truck was robbed outside a bank. The truck guard was killed in a shootout. There was a bandana collected from the crime scene. There was a small amount of DNA, 70 picograms. Normal amount for PCR might be 500 picograms or a nanogram. It was a 3-person mixture. TrueAllele pulled out the bandana genotypes, 3 of them, and comparing the 27% contributor compared with Johnson gave a likelihood ratio of 200. That's not on a log scale. That's 200. So that number has 2 zeros after the 1, 2 point something on a log scale. There was a Daubert hearing. TrueAllele was admitted. And then there was a hung jury. They had another one. There was a guilty verdict, 50-year sentence. Opposition argument. The main point of the opponent at the Daubert hearing was low LR values are unreliable. I testified in this one. His argument went nowhere. He was so desperate at the end, he was arguing high LR values were unreliable because what he was saying wasn't science. We used LR distributions to show why this wasn't so. Here are the 2 distributions. The non-contributors on the left, the contributors on the right. All these pictures were just generated in the TrueAllele distribution interface, which makes it a lot faster to prepare for court and presentations and papers. We just take them off the interface. What's the separation between the non-contributor and the contributor distribution? 99.97% is the accuracy. It's pretty good accuracy as a classifier. And for this score, beyond 2, we're seeing that we're not even in the overlap region. But this is clearly in the contributor range. The error rate under the non-contributor curve here is very low. And you're seeing that this score, the match statistic, is being classified as a contributor, not as a non-contributor. The non-contributor distribution, we can look at its tail probability to the right of where the match statistic is, and that will give us the error rate. It's just standard statistics. We reported the error rate. A match between the bandana and Johnson is 200 times more probable than a coincidence. That was in our report. It's giving the change in probability of the match or the genotype. We give an error rate. For a match strength of 200, only 1 in 4,000 people would match as strongly. And so we report that. Now there's a law about likelihood ratios that was known back in the 1950s. And the law is this. The error rate is less than 1 over the likelihood ratio. You have to change it and flip it if it's an exclusionary statistic. But for an inclusionary statistic, if you have a likelihood ratio of 1 over 200, you're guaranteed that the error rate must be less than or equal to 1 over 200. In this case, we calculated it. It was 1 over 4,000. If you consider how inaccurate eyewitness testimony is, and most everything you see, bite marks, most everything you see in forensics, an error rate of 1 in 4,000 is quite low. Is it clear that error rates are helpful? We will not report a likelihood ratio without an error rate. There's a whole philosophy about that. The FBI and other groups like using verbal equivalence. A verbal equivalent is kind of like saying, well, your speed was measured by radar by a police officer, and they go to court, and instead of saying to the jury or the magistrate how fast you were going, they say, you were going fast, or you were going really fast, or you were going kind of fast, and they refuse to give a number. That doesn't really make sense if you can give a number and give an error rate. We find jurors actually understand strange concepts like probability, because it's not strange to humans at all. You deal with probability every day. Maybe it never rains in Virginia, so you don't have to worry about it, but people are used to probability. This case, another federal case, another Daubert hearing. This is the Sandoval case that was published in Thompson's paper. I'm using Sandoval's name with the permission of his defense attorney. His defense attorney was horrified when Thompson's paper was published before the case was resolved. And that paper published Sandoval's, the defendant's, DNA profile. You could contact the author for the reports that gave the defendant's name. It's kind of unusual to do that. The police out in California collect 2 baggies containing methamphetamine. The policeman claims they were under the defendant's arms, and that when he opened his arms, the baggies fell out. The defense didn't believe the police, and they had the baggies tested. They found DNA mixtures. The original private lab used their StarMix software on it. The federal prosecutor had a Daubert challenge against StarMix on the defense's evidence. And then TrueAllele got involved, and then there was a plea agreement that dropped the more serious charge of this possession. JFS published a very speculative case report by Thompson that tried to explain why the StarMix results were maybe not reliable, but more reliable than TrueAllele, because they got different answers. So let's go into what happened. Your professor, Dr. Mark Wilson, is co-author on the response we published about 1 year ago, April 2024. Here's the opposition argument. This is the crux of the Thompson paper. TrueAllele and StarMix, the OPG, other probabilistic, can give different likelihood ratio results. Because two different systems can give different results, probabilistic genotyping isn't reliable. Does that even make sense to you? If I get on an airplane and I fly to London, that's one thing. But if I get into my car and it doesn't take me past the shore of America, the car is unreliable. I mean, it's hard to grasp the argument that different systems are supposed to be giving the same answer when some systems aren't designed for it. Let's take a look at what was reported. The original result with 40 RFU looked at 24 data peaks, and they reported from the private lab a number like 1 in 25, which is negative 1.38 ban. Ban is just the units of log LRs in base 10. So negative 1 point something means it's going to be 1 over a number between 10 and 100. And then TrueAllele looked at 210 loci, doesn't have a threshold, and it got 1 in a million. And then this was run in StarMix by other people at different thresholds. At 20, it got a more negative statistic, exclusionary statistic than TrueAllele. Looking at less data at 90 with only 11 data peaks, it got something close to 0, negative a half ban. We actually did this as a study. We got a complete spectrum. As you gave StarMix more and more data, it got stronger statistics. As you gave it less data, it got weaker statistics. Of course, that hasn't been validated out here, and there's no reason to think that any of these numbers are accurate. But it would depend on how much data it saw. If you're taking a look at a two-person mixture at over 20 loci, and you're generally going to have 3 or 4 peaks, how could you possibly get an answer with 24 data peaks that even means anything? And it was just kind of defied comprehension that this was even a question. Let's look at distributions. Here's TrueAllele. No analytical threshold over 200 data peaks. On the left is the non-contributor distribution. On the right is the contributor distribution. On the baggy evidence in this case. So what this is showing you that any positive match statistic would indicate a contributor classification, and any negative log LR would indicate a non-contributor classification. The accuracy is 100%, is 1. That's the A value. It's really a perfect classifier again. Are we near 0? Is this a problem? Are we even concerned about a 1 in a million possibility? No, because the match statistic is at -6. And the error rate from the contributor distribution is so low at that point that there's nothing to talk about. The area under the curve to the left of the right bell distribution, there's just nothing there. Are you comfortable that Sandoval is not in this evidence, looking at these distributions? We have a negative classification result and very good separation. But now let's take a look at StarMix. Same scale. We're still going from -20 out to +20. What we see is an information collapse. At the reported value with 40 RFU, a log LR of -1.5, this is what we're seeing. That green is the reported match statistic. The contributor distribution is close to 0 to the right. The non-contributor distribution is close to 0 to the left. Moreover, they completely overlap in the region where this match statistic is being reported. Does that look very reliable to you for criminal justice? So this is what the argument was about without having distributions to argue. So you're basically getting an information collapse from a perfect classifier to a classifier with a 10% error rate. This is what the whole thing was about, which scientifically isn't really much. It also shows the power of these distributions in explaining why some systems on the data will give output that can classify, and other systems that don't have as much mathematical modeling or use as much of the data will not get as much information. Its expected information is in those distributions. There was no Daubert outcome on that. The prosecutor gave up and agreed to a plea from the defense. This is another case. This was a federal defense case we happened to be working on with the federal defenders. And here, a shooting homicide in Washington, D.C., a gun and a magazine are recovered as evidence. They are low-level mixtures, 6% component of a 3-person mixture. The magazine of the gun is a 2% component of a 4-person mixture. Conventional forensic DNA analysis failed. We got the case. And this is what we found. On the gun, the log LR is -7 point something, so that's a number less than 1 in a million. And the log of the error rate is -11, which is close to about almost like 1 in a trillion. On the magazine, the log LR is -11, which is out to about 1 in a trillion. And the error rate, that is the area under the curve from the contributor distribution, it's about negative, say 15 or so. Again, that's less than 1 in a trillion. So we didn't think there was any issue with this based on what we know about the science validation studies. The federal prosecutor requested a Daubert hearing. They got a defense attack which was to replace all this quantitative work of quantitative likelihood ratios, error distributions, with old-style binary logic. The argument was so atrocious that it was the first case we ever won on the papers, quote, where the judge didn't even bother with a hearing and just ruled truly ill-admissible. I should point out that this argument is the key feature of Thompson's rebuttal to the response that Mark and I and Nasser wrote. He recapitulates the whole argument, but he doesn't mention the problem. So here's the argument. TrueAllele's own validation study shows high log L error rates, therefore it's not reliable. Well, LR distributions show this isn't true. Again. So the attack was on this paper we wrote with California Lab. Kevin Miller was the director at the time. And Jennifer, who gave the talk, is another co-author. And this paper was published 10 years ago. It was the first paper that showed that you could separate reliably DNA mixtures on up to 5 unknown contributors. TrueAllele is still the only system that does that routinely. Here's the opposition argument. Let's pretend that LRs are binary. The number is either less than 1 or greater than 1, or the log is less than 0 or greater than 0. Now, in the actual software version of this case, not in what was in the paper, we take the argument, here's a mixture range of 1 to 5%, 5 to 10%, and now we're counting. We're not looking at distributions. It's all binary. The count for LRs less than 1, for 7 out of 20 events is 35%, and for 0 out of 17 is 0%. The binary argument is twofold. One is, we knew there was a 35% error rate, and so it's unreliable. Not only did we know it, but we didn't disclose it to our horrible people. That's basically what the motion said. However, these binary error rates are simplistic and irrelevant. The likelihood ratio is quantitative. The score is quantitative. You get back a glucose test from the doctor. It doesn't say yes or no. It gives you a number. It's something to think about. What's the score? The same thing with likelihood ratios. The error rate depends on the LR magnitude. Why? Because the further you go to the extremes, away from 0, the smaller the area under the curve. So the error rate depends on magnitude, both on first principles and inequalities, and just based on what an error rate is as area under the curve. Here we showed that in the case with mixture weights of 5 and 2.5%, these are the log LRs, and those are the log of the error rates. In the validation study, these were the log LRs, which tend to be much smaller, and the error rates are also much smaller. So that's what we're seeing, looking at the actual distributions. Now, if we take those numbers and plot them, So for the gun, here are the distributions. What do we see on the distributions for TrueAllele? On the output genotype for the gun in this case, this is what we found. And now what is the contributor distribution for this contributor in the gun? Well, there's the distribution on the right. What's the non-contributor distribution? Classifying negative scores. It's this bell curve on the left. That's what the software produced from TrueAllele. And green is what the match statistic was. The classification accuracy is 100%. It's 1. It's a perfect classifier. You would not expect that a match statistic of -8 on a log LR score, 10 to the -8, is going to cause any difficulty with this classifier. And here overlain on the figure are from this other validation study that used a different version of the software. It's around 0, and it's not related to this evidence. And we saw the same thing with the magazine. Here, the classification accuracy was 99.99%. Those are the two curves. You see, if you had a statistic a little around 0, you'd have to really look at the error rates. But this was like -12, 1 in a trillion. There's no issue. Think of that. What is the error rate of this contributor curve as that tail goes all the way to the left? And you look at the area underneath it. Well, I told you, it's like 1 over 10 to the 15. Very small error rate. You want to be using quantitative scores and not artificially look at everything around 0 that's not relevant. And the distributions help. They visually show you, they give you the accuracy of the classification, and they also give you the error rates. When you get these unfounded attacks on better science that uses probability and probability modeling, here is how we respond. Well, use a fully Bayesian system like TrueAllele that uses all the data without thresholds. Let it separate the mixtures into accurate contributor genotypes. We report everything we find, inclusionary and exclusionary, and we use LR distributions to give LR error rates. Many times people will not report exclusionary results. They won't report inclusionary results. Maybe it makes sense with systems that can't report there, but it certainly doesn't make sense with systems that accurately classify. And of course, respond to bad arguments with good science.